Good morning everyone and welcome to the NPTEL course Advanced Distribution System Analysis and Operation. We are continuing with our module 8, which is DER Integrated Distribution Network Fault Analysis and Protection. Okay, till the last class we have seen what are the impacts of the DER integration with the fault currents on the fault current, and also we have seen how we can classify the faults with the help of traditional and as well as your AI based techniques. What are the methods? So, today we will see another aspect, that is called relay coordination algorithm. That means how you can coordinate the operation of the primary and the backup relays to clear a fault. So, what is relay coordination? Relay coordination refers to the systematic setting and timing of the protective relays, especially for overcurrent relay normally we see. That means, if one primary relay, that is, let us say this is the system and you have different relays installed here. This is, let us say this is R1, this is R2, this is R3. Now, if a fault occurs in this section, let us say this is AB section, BC section and CD section. If something happens to CD section, one fault occurred. So, what is the nearest relay which can disconnect the system, that your fault will be disconnected from the system, that is your R3. So, R3 will be the primary relay for this fault, and the operation of the R3 only will disconnect the CD section from the electrical circuit. But if the R3 fails to operate within a certain time limit, so at that time the next one, that is the R2 will operate to disconnect the fault. So, at that time BD, this entire section will be disconnected from the electrical circuit. So, the R2 will act as the backup or the first backup to this R3 relay, that if the R3 fails to operate, then R2 will operate. Again, if the R2 fails to operate, then R1 will operate. So, that is called the secondary backup or the second backup for the R3 relay. But you do not expect this R1, R2, R3 to be operated simultaneously, because if they operate simultaneously, then what will happen? All this AB, BC and CD section will be disconnected from the supply, though your AB and BC are the healthy sections, only your CD is the faulty section. So, you always expect that only CD will be disconnected, not the AB and BC. So, for that your R1 and R2 relay has to operate sometime later, and it can sense that your R3 or the primary relay has failed to operate, and at that time only I have to operate. So, that is called the relay coordination operation, and that depends upon how you are setting your R1, R2 and R3, depending upon the currents, depending upon the time of operations and henceforth. Okay. So, the nearest relay to the fault is the primary relay, and that has to operate first. A backup relay steps in only if the primary fails. It involves tuning two key parameters of directional overcurrent relay. If we go with the directional relay, because always we have seen that for reducing the effect of the bidirectional power flow, normal overcurrent relay is not a good option. So, now you have to go with the directional power flow, not with the bidirectional power flow. Bidirectional power flow relay, we have to go with the unidirectional power flow relay. That means, that will sense not only the amplitude of the current, also sense the direction of the current, and depending upon that it will operate. So, the settings are: first the pickup currents, the current threshold beyond which the relay will consider tripping. So, that is the threshold current limit, and time dial setting determines the delay before the relay trips after detecting a fault. So, if you have sensed the fault, but the setting, the time setting will be such that after, let us say 0.2 millisecond or 0.4 millisecond or 5 millisecond, it will operate depending upon the situation. Primary relay time delay setting will be very low, because it cannot spare the fault to be there for very long time. For backup relay, when it will act as a backup, the time setting will be little bit higher, and that must be more than the time setting of your primary relay. Then only it will act after the primary relay. Okay. So, then the microgrid operation depends upon the microgrid operation, obviously the grid connected and the islanded mode, and also with the DERs it has to sense the fault current, and then when you set the pickup current value or the time value, you have to keep in mind your system is grid connected or islanded. If it is grid connected, then the supply, how much supply it is taking from the main grid, and how much contribution it is taking from the DERs. And also in the islanded condition, how much only from the DERs it is getting from the as a fault current from the DERs. Then synchronous DERs is present or inverter based DERs is present, what is the ratio of that, and where is the location, this everything you have to keep in mind when you have to set the pickup current and the time delay setting input. What are the protection challenges? Traditional directional overcurrent relay struggle to detect low fault currents from converter based DERs. We have seen that for an inverter based or converter based DER, you have a fault current limiter inherent in the control loop of that inverter. So, for that case, if your fault current is already very low, so at that time your traditional relay setting or the pickup current setting cannot sense that fault, and then it cannot disconnect also that faulty events. So, that fault will persist. So, that is the primary challenge. Second challenge, issues include bidirectional fault current, sympathetic tripping and relay blinding, that we have discussed in our last class. Miscoordination occurs between primary and the backup relays due to variable fault current values, that we also have seen. Then relay coordination approaches. What are the relay coordination approaches? Relay settings involve the pickup and the time dial setting. The coordination is formulated as a non-linear programming, that we have to minimize the operation, time of operation of the both the relays, keeping into consideration that the primary relay should act before your backup relay. Okay? So, it is an optimization problem, minimization of the time, keeping some consideration, some constraint. So, that is an optimization problem, and that optimization problem is mostly a non-linear problem because of the value of this pickup current and the TDS, that we will see what is the expression. Otherwise, that you can with some linear programming assumption or linearization method, you can linearize them and then you can solve the IP and the TDS. So, your decision variables are your pickup current and your TDS, that is your setting. So, that is your decision variables. So, traditional methods are what? You can use fault current limiters, allow single relay setting for both modes, but may ignore relay operating time limits. So, you can put a fault current limiter for the relay before the relay, and that fault current limiter will reduce the current. So, and that will allow the relay to operate properly, but that will nothing to do with the time of the operation. Second, communication based strategies, the differential protection and the feedback fallback. That is the differential protection, we know that takes the data from the both the side and then compare, and then that is very good for when you go for the equipment protection. Or you can do the microprocessor based strategies with multi-mode and time grading, or hybrid adaptive differential protection for sensitive equipment. So, what is this adaptive overcurrent scheme? Overcurrent relays are very cost effective. So, generally whatever in distribution network as well, mainly that whatever application we go, we mainly see what improvisation we can adapt with the overcurrent relay or directional overcurrent relay to make them more robust, other than going for new fancy methods. Okay. So, in overcurrent adaptive scheme, use the positive negative sequence current components for relay coordination. We have seen that we can use the positive, negative and zero sequence component to get the fault classification. So, that current value you can use as well for the relay coordination, but that require high speed communication between relay, DG and the equipment agents. Eliminate need for central processor and voltage transformers, but introduce reliability uncertainties. Now, we will see a case study with the directional overcurrent relay coordination scheme for protection of microgrid. Okay. So, an adaptive protection for directional overcurrent relay coordination across grid connected, islanded, radial and a mesh configuration is considered, because we know that with the varying condition like grid connected or islanded, it is a radial network or a mesh network, depend upon the architecture, depend upon the connection, your fault current keeps on changing. So, your setting of the relay setting should be adaptive or should be robust enough that it can take this entire situation into consideration in when it will go for the fault detection and the classification and as well as relay coordination. So, considers multiple external grid connection points for improved reliability. uses both offline pre-calculated relay settings and online real-time updates of that operation when it will go for the fault relay coordination problem or relay coordination. Formulates coordination problem as a nonlinear constraint optimization problem. Okay. So, your overcurrent relay coordination problem looks like this. The objective of the coordination problem is to minimize the sum of the operating time. So, you can see it is the objective is to minimize the total operation time of the primary relay by maintaining sensitivity and selectivity of the clearing faults, and the objective function is as follows. So, this will be minimize the total primary relay time operation of time, keeping that your pickup current will be within its minimum and the maximum value. Your TDS should be also minimum and the maximum value. Your time of operation of the primary relays should be also from the minimum and the maximum value. And also this is the coordination equation that will keep that your backup relay, the time of operation of the backup relay minus the time of operation of the primary relay should be greater than minimum coordination time. So, you have to choose that minimum coordination time, and depending upon that your operation time of the backup and the primary relay will be decided. Okay. So, that normally in the overcurrent we follow the inverse definite minimum time characteristics, and with that characteristics the time of operation of overcurrent relay depending upon the pickup current setting and the fault current setting, this gives with this equation. It is a nonlinear equation. That is why we told that your relay coordination optimization problem is a nonlinear optimization problem, because you have to set this equation to your objective function. Only operating time of the primary relay, but there is no restriction on the operating on the backup relay. So, if you go to this equation, it is only minimizing the operation of the primary relay. So, and keeping this into consideration, it will obey, let us say that primary relay fails to operate, and to obey this, then let us say you fixed your MCT to be 2 millisecond. That after 2 millisecond, if the primary relay do not clear the fault, then backup relay will operate. That means this equation. So, that does not mean your backup relay will operate just after the 2 millisecond. It may possible it is operating after 5 seconds or 10 seconds. It is obeying, because mathematics that is fine, but physically that is not fine. So, then you have to perturb or you have to revise your objective function. So, then it will go, if you do not revise this, then backup relay will operate in a higher operating time and that larger value of coordination time interval. Okay. This affects the selectivity and sensitivity of the relays, and that leads to unreliable operation of the microgrid during fault condition. So, how you can revise that objective function? By not only reducing the primary relay operation, you will also reduce the backup relay operation. You have to minimize the total sum of that time. But if you do that, then it is a tendency that backup relay will operate with the primary relay itself. So, to keep that also in mind, that your backup relay will act as a backup, not as the primary, you have to introduce another component, that is your error component. And what is that error? That error will say this like difference between your backup time minus your primary time operation minus your that minimum coordination time, that should be reduced. So, ideally that should be equals to 0. If that is 0, so at that time you can say that your epsilon is, then your objective function is minimized. So, you have obeyed your minimum time operation for your primary relay, you obeyed your minimum time operation for your backup relay, but your backup relay, the time difference between backup relay and the minimum primary relay is also restored with your minimum coordination time. So, the sensitivity analysis is performed to know sensitivity of the backup relays, for it is expressed by this equation. Okay? And that sensitivity value, that depends upon your fault current, your maximum load current, and that has to be greater than a threshold value beta. That threshold you will set, and if your sensitivity is greater than that, then you will say my operation is good. If it is not, then you will say something is bad happening, I have to change my setting, I have to change my strategy. So, this is the test system. This is a 7 bus microgrid setup of 13.2 kilovolt. It has two grid connection, one is two PCC points for connecting the grid. It is a both side feeding microgrid. One 5.5 MVA synchronous generator is present. This is your this one, maybe a diesel generator or a micro turbine. You have a solar power plant in this bus B3. You have 2 megawatt of wind generation at bus B5. Then you have 14 directional loads, that is your R1 to R14. You have 7 loading points, L1 to L7. Then you have 4 switches. This S1, SW1, your S2, SW2 and S1. Depending upon that, with this S1 and S2, you can change the PCC point, like you can go with the 1 PCC point, 2 PCC point, depending upon that the switches operate. And this SW1 and SW2, that will give that whether your system will operate as a radial network or as a mesh network, depending upon the connection of the or operating status, switching status of the SW1 and SW2. So, switch status determine the current operating state, that is radial or mesh, grid connected or islanded. If you open both the S1 and S2, then you will get islanded operation. If you just connect with one, then you have only one PCC point, or if you connect the both, then you have two PCC point. So, 7 fault locations has been identified, that is F7, F4, F2, these locations has been identified and those are simulated. So, first the offline operation, that means before the fault occurs, your relays has to be set to a certain value, pickup and the TDS value. So, that is an offline calculation. So, the critical operating states like the grid connected islanded modes are analyzed. Studies include load flow and the fault analysis to determine. So, you do your load analysis, that will give you the loading operation, loading current value, and then you do the fault calculation and you will get the fault current value. So, depending upon the maximum load current and minimum and maximum fault current, you do your relay setting. Because the relay setting, current setting should be such that it should be more than the maximum loading, but lesser than your minimum fault current. So, this is how we fine tune the threshold value setting of the overcurrent relays. So, each setting group is correspond to a specific operating state. So, you keep different PCC connection, you keep the radial or the mesh network, and depending upon that you determine the pickup and the TDS value settings. Then you come to the online. So, in the online what you will do? The central controller of that microgrid or the distribution network continuously monitor the switching status of the DOCRs, DERs and the grid connection points. That means your SW1, S1 and S2 and SW2 that are continuously monitored, whether it is a radial or meshed or your 1 PCC point or 2 PCC point, or even it is operating at the islanded mode. If the detected operating state matches one of the pre-stored state, that means you already simulated in the offline multiple scenarios with multiple loading condition, multiple faulted level condition. So, if at the online something is matching, your scenario is exactly matching with your pre-stored or your offline cases, then just your overcurrent, directional overcurrent setting will be that corresponding setting. Okay? But if it is not, a pre-stored, then you set it to a most suitable one. Okay? Like if it is an, let us say fault current is there, fault impedance is somehow different, but it is an islanded mode or grid connected with only one PCC mode. So, fall to that category. Then calculate the fault current for the current condition. Okay. Then verify the relay coordination with the fallback setting. With whatever settings you have calculated previously pre-stored, with that new fault current condition, see whether your relay settings are obeying that coordination of principle or not. If the coordination is valid, continue using the fallback setting. If the coordination is restored, that means whatever is desirable that you are getting, then you need not to go with a new setting process. Whatever setting you have, you can just use it. But if it is not, then recalculate the new setting with the current state. Then you solve your optimization process and calculate the new setting. This process repeats automatically for any further operational changes in the microgrid. So, this is the overall algorithm where offline study and the online studies is carried out, what we just discussed, and this is designed to handle the DOCR coordination across various microgrid operating states with offline and the online. So, now we will go for the testing. So, 7 faults are simulated at the midpoints of the feeder to evaluate the protection response. Primary and the backup relays are identified. Depending upon that, the current setting, current transformer ratios has been defined for the maximum loading current, and those are given to this table. Similarly, for the adaptive protection scheme, the relay operating states for different your connections, grid connected or the islanded connection with the switches of switch operation, your settings has been identified and those has been listed out, or those has been stored, pre-stored data you have. Then after that, what you will do? You will go with the your islanded mode or the grid connected mode, depending upon that with the relay setting as a meshed connection or the radial connection. Previously, you do with the all the radial connection, then you go with the meshed connection, do the same process. Do the same process with the meshed connection for GM1, GM2 and radial connection with your islanded mode condition. Okay. Do that and save the same your IP value and the TDS value you calculate and stored it as a pre-chart with your system. Now, you do the actual online operation. These are your offline settings that you did and you stored them with your system. Okay. Now, do the online. So, and compare if you go with an adaptive setting, then what will happen, and if you go with a fixed setting, then what will happen. If you go with a fixed setting, let us say you go with only with the GM1 setting. What is that GM1? GM1 is the grid connected mode only with your PCC1. If you only go with this setting, that you do not change your setting depending upon the situation, you can see obviously GM1 is no miscoordination, but GM2 you will see that 10 miscoordination for mesh condition and 6 miscoordination for radial. Similarly, for GCM, that means when it is a grid connected mode with both the PCCs, if that is the case, then you have 7 miscoordination. If it is islanded mode, then you have 6 miscoordination. So, you have always miscoordination with the different settings. If it is online, if you incur a different settings and you have something else at your pre-specified setting in your overcurrent relay. So, if your overcurrent relay setting is not changing with the time considering the situation of the system, then you will always see, for if it is an exactly same core system or exactly same situation, then coordination is very good. But it's some, if it deviates, even the connection or the configuration of the network little bit deviates from its pre-specified condition, at that time your coordination will be completely spoiled. But if you go with the adaptive setting, so at that time you can see with every changes your system is changing and searching whatever the pre-stored value, and depending upon that it is selecting its operating states. So, at that time you can see there is no miscoordination. So, with adaptive setting there is 0 miscoordination in all operating modes. From the result, it is concluded that the adaptive scheme has ability to mitigate miscoordination of directional overcurrent relays and provide adequate protection to microgrid in all operating states. So, whenever with the DERs, if you go with the relay coordination, because with the DERs your system configuration or system connection with the main upper grid can changes rapidly. So, if you have a DER, so at that time you cannot go with a fixed setting for your overcurrent relays for the as far as the coordination problem is concerned. So, at that time you have to go with the adaptive setting that will keeps on changing depending upon the system situation. With that, I will conclude today's lecture and will continue with this protection schemes in the next lecture. Thank you.